there's one more application of the definite integral that we want to take a look at, and that application is to arc length. So here's the basic premise. You have some curve. It's a curve. And you want to figure out how long is that curve. So you think to yourself, well, what if it were just a line segment? If it were just a line segment, we would figure out its length by figuring out the change in x and the change in y, and we'd say it's approximately the square root of change in x squared plus change in y squared. You're like, yeah, but that's just one segment. I mean, surely we could do better. Maybe we could do 1, 2, 3, 4 segments. And then if we do 4 segments, well, then the arc length is approximately the sum of 4 segments, each of whose length is the square root of delta x sub k squared plus delta y sub k squared, right? And you're like, yeah, but that's just 4 segments. What if we had lots of segments? What if we had n segments, and the distance each time was the square root of delta x sub k squared plus delta y sub k squared? Then you'd start thinking to yourself, wait a second, I know where this goes. There are n of them. We let n get very, very large. We take a whole bunch of really, really small segments going all the way around. I've seen the guy do this before. This is how this works. We take a limit as n goes to infinity. It turns into an integral. Except that what's the thing that's always hanging out over here, right? There's always a delta x sub k hanging out over here that turns into a dx when we make an integral. So we've got to allow for that. And the way we allow for that is we divide by delta x. Now, you and I both know that this is dividing by delta x squared, but it's under a square root. So we're dividing by the square root of delta x squared, and that neutralizes this delta x here. This is a Riemann sum. And so as n goes to infinity, we get arc length. It's an integral from a to b, where this is a and this is b, of what? Of the square root of, this is 1, this is delta y over delta x. That's a dx. This is the arc length integral. This integral will find arc length for any curve for which dy dx is defined across the interval. For example, let's take y equals x to the 3 halves from 0 to 8. Let's find its arc length. Well, how do we do that? Arc length is the integral from a to b of the square root of 1 plus derivative squared dx. Well, what's the derivative? The derivative is 3 halves x to the 1 half. And that means that this is the integral from 0 to 8 of the square root of 1 plus 9/4 x dx. So we let u be 1 plus 9/4 x. I don't want to be 1 plus 9/4 x. Well, too bad. That's what u is. And then this becomes 4/9 times the integral from 1 to 19 of the square root of u du. We know what the antiderivative of u to the 1/2 is. And sure enough, this is 8/27 of 19 to the 3/2 minus 1. This is a very strange number. This is a very convenient integral. Most of the time, you'll be able to set up an arc length integral, and then you will have to use technology to evaluate it. Most of the time, that's what happens. Oh, not yet. If I may, can we talk about the strange possibility? This is x to the 2/3. So that's the 0.84. Finding arc length here is dicey. And it's dicey because you want to set up an integral that has a dy dx in it, but dy dx is not defined there. And because dy dx is not defined there, we change gears. And we do the square root of 1 plus dx dy squared dy from the bottom to the top. Because dx dy does exist all the way across, because dy dx is never 0. So we do the integral from 0 to 4 of the square root of 1 plus dx dy squared dy. Well, x is y to the 3/2, so dx dy is 3/2 y to the 1/2. This turns out to be a similar integral to the one we just did, and for reasons that you can confirm, it turns into this nice number. Okay, I hope that this is helpful. There will be a video with a couple of examples in it to drive home the point and to help you in your studies.